Okay, so now we're going to start doing some calculus on these parametric surfaces. So first, let me talk about grid lines on parametric surfaces. So I want you to imagine that we have a parametric surface and the parameter space off to the left. So let's say that there's some sort of domain of the vector function that is the parametric surface. And then, I don't know, the surface looks something like this. Okay, so this over here is the image of RUV. And what I want you to imagine is fixing a particular parameter value. So let's say we fix a value of V. And I want to imagine all of the other associated inputs to the vector function and what the image on the surface looks like. So it's going to be like a line over here on the surface. So this right here is the image of V naught, and U is varying over the parameter space in the UV plane, and I'm gathering together all of the outputs associated with V naught. And then of course I could do the same for a U naught, a fixed U value, allowing the V parameter to range, and I would get myself another grid line like that, and this would look like our U naught V. And then we get a whole grid by fixing various U and V values. And it's usually these grid lines that are really helpful in understanding the geometry of the surface, seeing how it looks. Okay, and I'm going to ask a question about tangent vectors in a second, but I want quickly to think about a specific example that's familiar. So, like if you have parameterized the surface of a sphere where V is acting like the theta and U is acting like the phi, we've done that previously in this slides, then what we originally said about spherical coordinates corresponds to this discussion of grid lines. So V is the theta variable, and those grid lines fixing a particular V value or theta value correspond to longitude lines. So like V equals 0 is this longitude line that I just drew with theta equals 0. And then as I go around, I increase the theta from 0 to 2 pi, I get all of the longitude lines like that. And then the phi, or the U in this case, correspond to latitude lines. Okay, so you could imagine fixing phi or U equals pi over 2, and that would correspond to the equator right here. So when we draw these grid lines, again, it helps us get a visualization of the surface, but it also gives us a sense of wrapping. Like I can imagine the parameter space as like wrapping paper, and when I pick it up and I would have to sort of rotate it and then wrap it around this globe, and I get this sort of geometric interpretation about how the function works. It takes that parameter space, every single point in the parameter space, and it sort of attaches it to a point on the surface of the sphere, and that feels like a sort of a wrapping of the parameter space onto the surface. Okay, now let me try and answer the question that's asked here. What is a tangent vector to a U curve? So let me come to either of these images. If I look at, let me start with U curve. So this right here, when I fix a V value, the U parameter is allowed to vary over the parameter space. So when I fix a V value, I'm defining a U curve, all right? These are curves on the surface that come from lines that are parallel to the U axis. So if I come over here and look at that and fix your favorite point, let's fix a point U naught V naught right here. And the question is, what is the tangent vector to this U curve at a given point? And if you think about it, this function right here, since I fixed the V value, it becomes a one parameter curve. So I can view it as just a regular old vector function with one parameter. So I could call this G V naught of U. And we know how to find tangent vectors to parametric curves like this. We just take a derivative, right? This would just be G prime. A tangent vector, let me put it in a different color. So a tangent vector, I'll draw it here. That would be G prime like that. So as far as the two-parameter vector function that describes the surface is concerned, to express that particular derivative that represents a tangent vector, I'm taking a partial derivative of the two-parameter vector function because I'm holding v constant and I'm taking a derivative with respect to u. So this vector right here can also be expressed as the partial derivative with respect to u of the two-parameter vector function at u naught v naught. So that right there is an expression for the tangent vector of a u curve. Okay, similarly, when we have fixed a u value, because I'm doing this in green, then that defines what we're calling a v curve. So a v curve is a grid line that results from selecting a line in the parameter space parallel to the v axis. So if I come over to the picture and I ask, okay, well, what about a tangent vector to that curve? Well, since u is being fixed at u naught, I can imagine that u curve as a one parameter vector function, so h u naught of v, and the tangent vector is going to be the derivative of that. So as a one variable function, that tangent vector is h prime u naught at v naught. I think I forgot a naught over there when I said, oh, sorry, not that. Okay, and so what is that in terms of our two-parameter vector function that represents a surface? Well, holding u constant at u naught and taking a derivative with respect to v is a partial derivative. So the tangent vector there can be expressed as r sub v at u naught v naught. So this vector and this vector are two tangent vectors to the surface at the point u naught v naught. One going in the direction of the u curve, and one going in the direction of the v curves. Okay, so what are we going to do with these tangent vectors? Since r sub u and r sub v are tangent to the surface at this point, then I can create a normal vector to the surface if I cross them, right? So these two vectors are tangent. When you take a cross product, it makes a perpendicular vector, and that's going to produce for us a normal vector to the surface, like this. And like the direction it points depends on how these curves are parameterized. Like what I've indicated in the picture here is that as I increase the u parameter, for example, the surface, or you move along the u line in this direction, so the derivative is pointing in this way. It very well may be the case that as you increase the v value along a v curve, that that you trace the v curve in this direction, in which case the purple vector would be pointing this way and the normal vector would be pointing down. But in any case, you do get a perpendicular vector to the surface when you take r sub u cross r sub v. Okay, so if we have a particularly nice surface, one in which the parameterization is smooth, so you've got the partial derivatives that you need, r sub u and r sub v, then you're going to have a notion of a normal vector anywhere on the surface, and those surfaces are going to be good to do calculus with, basically. So let me proceed thinking about a surface that satisfies that, and let's think about how to compute surface area using a parameterization. And this is going to be a fundamental concept, not just to compute surface area, but also to develop the notion of a surface integral. Okay, so this is what we need to do. We need to quantify the amount of surface area resulting from a very small change in both of the parameters in the parameter space. So again, I'm going to set up a surface that is parameterized by some region in the parameter space. And I want to fix a point of interest, u naught v naught. Okay, and here's its image over here. And I want to just increase the u parameter a little bit and the v parameter a little bit and make a little delta u, delta v rectangle in the parameter space. And then I want to look at the image over here. So this is like the little piece of the surface that results from that range in the parameter space. And I want to quantify that area. So I've just expressed some tangent vectors to the surface at a point u naught v naught. Which direction did I have them going? Let me just copy what I have. That would be ru. Okay, and so although the surface could be like wavy and stuff, it doesn't need to be completely flat there. A flat parallelogram formed by a certain combination of these tangent vectors would approximate the area of the surface right there. So, I mean, these vectors might be a little bit longer. Actually, I might even want to draw it like that so you get a sense for that. But I want to think about constructing a parallelogram, a kind of flat parallelogram from these two tangent vectors of appropriate length, given that the green part results from just a little delta u, delta v, and that's going to serve as an approximation for the area of this little bit of the surface. So if I take ru at u naught, v naught, and I scale it by the appropriate length, so in this case, I'm going to omit the inputs u naught, v naught, I scale it by delta u, then that is going to give me sort of exactly the right length and direction of a side of a parallelogram that can approximate the green surface area. And then likewise with the RV vector, this here will give me an appropriate parallelogram. So let me sort of redraw this. I've got a little bit of the surface. I'm zooming in here. And then I have an RU delta U vector, RV delta V vector, and an RU delta U vector. And when I form a parallelogram with those two vectors, it's going to form like this flat surface, but when delta U and delta V are very small, they're nearly indistinguishable, the flat parallelogram and the curvy piece of the surface that it's trying to approximate. So the area of the parallelogram that's formed by those two vectors, of course, is, we know from the cross product section, it's this cross this, again, omitting the inputs u naught, v naught in both cases. And the delta v and the delta u are scalar quantities that can be factored out, like this. And so the total surface area of the parametric surface is going to be the sum of all of the individual pieces that are constructed by chopping up the parameter space into a billion little rectangles. And this is our standard construction when we're building some sort of integral formula, right? So you take the parameter space, you chop it into a million rectangles by, selecting a delta U, delta V precision, and then you go over to the surface and you replace each of the little pieces of the surface with appropriate parallelograms, and you add them all up. You add up the areas that are looking like this. And that gives you an estimate for the total surface area over the parameter space. And of course, as you sort of take a limit of the, as the size of delta U and delta V goes to 0, then you get the actual surface area. So it will end up looking like this. Okay, so we have ourselves a sort of double integral formula to compute surface area of a parametric surface.